Gentlemen, good evening. Today, I want us to read through this article by Dijkstra, Programming as a Discipline of Mathematical Nature. This is EWD361. If you're not familiar with the EWDs, Dijkstra was what you'd call a pre-internet blogger. He used to write up these articles, sometimes by hand, and later on he experimented with a typewriter and he'd send them around. And actually, the kernel of most of the ideas that appears in his large articles and his monographs and books is in these EWDs. So these are highly scientific, but they're usually very approachable, and he worked on that. And in reading this, hope you get a good taste of the man's thinking. Here he is. And the reason I'm reading, you can find these on the University of Texas website. UTexas, I believe that's University of Texas at Austin. Most of them have been transcribed, but some are still in PDF form. But I want to read from the, as much as possible, get as close as we can to Dijkstra. So when it's handwritten, it's a bit more intimate. But now we have a typewritten article, which at least we can imagine that he laid his eyes on this article and he typed it with his own hands, or someone typed it for him. Programming as a discipline of mathematical nature. In this article, I intend to present programming as a mathematical activity without taking the arduous task of supplying a definition of mathematics pleasing all mathematicians, nor of defining programming in a way that is palatable to all programmers. So there's a lot of dry wit in what Dijkstra writes, but definitely these are two terms that are actually hard to define and distinguish from one another. With respect to mathematics, I believe, however, that most of us can heartily agree the following characteristics of most mathematical work. Number one, compared with other fields of intellectual activity, mathematical assertions tend to be unusually precise. Number two, mathematical assertions tend to be general in the sense that they are applicable to a large, often infinite, class of instances. And number three, mathematics embodies a discipline of reasoning, allowing such assertions to be made with an unusually high confidence level. So here he's kind of giving us a definition of mathematics, but it's a bit, like he says, he's not trying to give a full definition. It's kind of a description, some attributes, and it's true that in math, the statements are usually extraordinarily precise, and mathematicians strive to be general. And mathematics, since it's the art of reasoning well, the assertions that are made once you arrive through them in what is called formal reasoning, they tend to be very, very certain. However, the only thing is you have to figure out certain about what, because they're very precise. But let's read on. The mathematical method derives its power from the combination of all these three characteristics. Conversely, when an intellectual activity displays these three characteristics to a strong degree, I feel justified in calling it an activity of mathematical nature, independent of the question whether its subject matter is familiar to most mathematicians. In other words, I grant the predicate mathematical nature rather on the quo modo than on the quod. Now, when he says this, he's using Latin terms, of course. Quo modo means how, in what way, and then quod means what. So he's saying that programming, when you really understand it, is very much mathematical. And it's mathematical not because, first and foremost, it's about sets and groups and algebraic structures or topological structures or combinatorial structures or anything like this, even though those may come into it. But the nature of the way you have to reason to program effectively. So the quo modo, how are you thinking? In what way are you reasoning? Rather than the quod, which is the subject matter. He's saying it's about the form, formal, if we can use that adjective, that the form of reasoning about programming and proper programming is mathematical. A programmer designs algorithms intended for mechanical execution intended to control existing or conceivable computing equipment. These, usually electronic devices, derive their power from two basic characteristics. He's talking about computers. So where do they get their power? Firstly, the amount of information they can store and the amount of processing that they can perform in a reasonably short time are both large beyond imagination. And as a result, what computers could do for us has outgrown its basic triviality by several orders of magnitude. Secondly, as executors of algorithms, they are reliable and obedient. Again, beyond imagination, as a rule, they indeed behave exactly as instructed. These are two deep points. The first is just the processing power of computers. Of course, he's writing in the 70s, in 1973. And here in 2026, the power of the machines we have is terrifying. I mean, ordinary laptops now have teraflops of computing power. Teraflops meaning that 1 trillion calculations can be done per second by an ordinary laptop that you may have, that you may be with. And so, of course, you can't imagine all those calculations. But the second point is stronger, in my opinion, which is that they're very obedient. Computers do precisely what you instruct them to do. Now, this is true of traditional computers, deterministic machines. Of course, LLMs are changing this to an extent, but this is our focus here. This obedience makes heavy demands on the accuracy with which the programmer has instructed the machine. If the instructions were to produce nonsense, the machine will produce nonsense. Inexperienced programmers often blame the machinery for its strict obedience, for the impossibility to appeal to the machine's common sense. More experienced programmers realize that it is exactly its strict obedience that enables us to use it reliably, to forge it into a sophisticated tool that we would never be able to build if the executor of our algorithm had the uncontrolled freedom to interpret our instructions in quote-unquote the most plausible way. As a result, the competent programmer does not regard precision and accuracy as mean virtues. He knows he could not work without them. And this is very important because if you think about formal mathematics, so-called formal mathematics, most mathematicians talk about formal reasoning, formal mathematics. But in reality, the work they do is done on paper and pen, on blackboards, and they only asymptotically approach formalism for the most part, except for when they're doing some explicit calculations. And this is because it's all driven by human beings. And human beings are so intuitive, and we are so quick to supply assumptions. We're so quick to make intuitive leaps that computers do not make. And this, Dijkstra is saying, is not a negative thing for computers, but it's what enables us to write programs formally. You see, if you don't have a computer at your disposal, you can't know if your reasoning is formal, because you may deceive yourself into thinking that you've written a complete set of instructions that are unambiguous. But really, you're supplying some measure of intuition, or whoever you show it to, no matter how many people you give it to. All these people may be supplying you, there may be intuitive leaps that are taken, but as soon as you bring in a deterministic machine, there is no more intuitive leap. And until you make every instruction absolutely unambiguous and precise, nothing will work. So here we go. So there's the obedience. His work is also always general. So to be clear, we talked about precision. So he was talking about precision over here as the first characteristic of mathematical reasoning, and he's talked about how precise we have to be to program. Now the second criterion, he said generality. His work, the programmer's work, is also always general in the sense that each program is able to evoke as many different computations as we can supply it with different input data. Whenever we make an assertion about a program, it is an assertion about the whole class of possible computations that could be evoked under control of it, and designing an algorithm is nothing more nor less than designing a whole class of computations. So the programmer's work also shares the second characteristic. So what the extra is saying here, I've just opened a file over here and just put a basic, hello world program. But here I'm just printing out the first argument that you'd supply. You take a program like this, very simple program, right? But basically, this program, we can say, will print out whatever string you supply as the command line argument next to it. So if you supply XXX, it's going to say hello XXX. If you supply hello world, if you supply world, it's going to print out hello world when you run it. So the programmer's work, so this is what is meant by when you're saying that it can evoke as many different computations as we can supply it with different input data. This program here is like a mathematical operator. It's like a mapping, or it's like a function, in that it has a very large domain, a very large class of various inputs that it can take, even though it's short. And you can describe what it will do, but there's a nearly infinite number of strings you can supply it. So the programmer's work is also like mathematicians, in the sense that he's designing a large class of computations. Finally, what about the confidence level of his work? Well, it should be very high for two reasons. Let me just bring back the image up. Firstly, a large sophisticated program can only be made by a careful application of the rule divide and conquer, and as such consists of many components, say n. So you can only make a large program if you modularize. If you modularize your data structures, if you modularize your functions, you can only effectively organize your thinking if you break it down into components. And indeed, even those individual components tend to be broken down further. You'll have individual lines in each function, and within those lines you may have multiple different operations that are occurring. So like, even if you go back over here, you'll note we have this string here, and then we have argv1, and then we're calling printf. So there's different components over here, and the meaning of each has to be considered separately. But this is a simple example. A large sophisticated program can only be made by a careful application of the rule divide and conquer, and as such consists of many components, say n. If, however, p is the probability of an individual component being correct, then the probability p of the whole aggregate being correct satisfies something like p is less than or equal to p to the n. In other words, unless p is indistinguishable from 1, for large n, the value of p will be indistinguishable from 0. And what he's saying here is very easy to understand intuitively if we take a calculator over here. So he's saying that each of the components in a program will have a probability of having some kind of error in them as you're constructing it. Now, if we simplify the situation and say, let p be the average probability, or maybe a mathematician will tell us you don't just want the usual mean, you want is it a geometric mean, because we're multiplying probabilities together. But we could even take p as the probability of, you could take your beta modules and then you could use the p from there. But the point is, if you have lowercase p being the probability that any individual component is correct, no matter how you take this mean. If you raise p to a very high n, if you have a very high exponent, you're going to get exponential decay. So let's say we believe we are constructing a program with 99% with components whose chance of error is very low. So 99% certainty that each component is correct. But now let's say we have 100 different components, let's say 100 functions. Then we're going to have a probability that the whole program is correct beneath 37%. And you can imagine in a program that has 50,000 lines and maybe 700 different functions, this gets very ugly. Let's just see what that looks like. Let's say we do, no, I'm actually not sure how to use this Google calculator. Let's just do backspace. Let's do 0.99, raise it to the 700th power. And look, we are beneath what is this? If we look at it as a percentage, well, that didn't really work. So let's just do it again. Let's say 0. Okay, well, you get the idea. Next time, I promise I'll get a better calculator application. 0.99 to the 700. And then we multiply that whole thing by 100. We're beneath 0.1%. And so you can see what he's saying. In other words, unless lowercase p, the probability of each individual component being wrong, is indistinguishable from 1, for large N, the value p, capital P, the probability that the whole program has no error, will be indistinguishable from 0. If we cannot design the components sufficiently well, it is vain to hope that their aggregate will work at all. Secondly, its confidence level should be very high if we as a society would like to rely upon the performance of the algorithm, and we do when we use machines for air traffic control, banking, patient care in hospitals, or earthquake prediction. And so this is what we call at Zermelo, we call this Dijkstra's law. We call this principle Dijkstra's law. So basically what he's saying is if you construct a program without proving the correctness of the program, it will have bugs, provided it's sufficiently long. And also, just by virtue of this calculation here, if the number of lines in the program tends to infinity, in this other case, we took 700 functions as an example, but let's say you have a program that has 1 million lines or more than 1 million lines, then by the same kind of reasoning, you're going to have probabilistically an infinite number of bugs in your program. And Dijkstra is saying here that we have programs that run in hospitals, we have our banking system, we have many different things depending on these programs. So if we want to be confident about them, we need to be able to make lowercase p indistinguishable from 1. We need to be able to be certain about the components of the programs that we're constructing. Now, honesty compels me to admit, Dijkstra continues, that today, on the average, the confidence level reached by the programming profession is not yet what it should be. On the contrary, from a historical point of view, this sorry state of affairs is only too understandable. The tradition of programming is very young. He's writing in 1973, 2-3 decades into the computing revolution. And sadly, even here in 2026, 50 years later, we know that nothing has changed really. The tradition of programming is very young and has still many traceable roots in the recent past, when machines were still rather small and programming was not yet such a problem. Before we had machines, programming was no problem at all. But in the last 10 to 15 years, the power of available machinery has grown at least with a factor of 1,000, thereby completely changing the scope of the programming profession. But old habits seldom die. The old technique was to make a program and then to subject it to a number of test cases where the answer was known, and when the test runs produced the correct result, this was taken as a sufficient ground for believing the program to be correct. Which, if you have a very small machine, you can basically exhaust the possibilities. But with growing sophistication, this assumption proved more and more unjustified, until some 5 years ago, it surfaced in the form of the software crisis. One of the first considerations of what was later to emerge as programming methodology was this question of confidence. How can we rely on our algorithms? An analysis of the situation quite forcibly showed that program testing, and this is Dijkstra's great line, an analysis of the situation quite forcibly showed that program testing can be used very convincingly to show the presence of bugs, but never to demonstrate their absence, because the number of cases one can actually try is absolutely negligible compared with the possible number of cases. The only way out was to prove the program to be correct. And it's interesting today, you'll note that when people are talking about LLMs and their belief that LLMs can actually write programs, one of the things they point to is tests. But tests are a laughably shallow way of analyzing a program. In fact, there's no way you can show using tests that a program lacks bugs, unless you are considering the program under a formal model that shows you that the precise tests that you wrote correspond to components of a theorem you're proving that shows that the program is correct. But in general, tests do not show the absence of bugs. They just show when the program has failed, but they don't show that the program is indeed correct. The suggestion, Dijkstra continues, that the correctness of programs could and should be established by proof was met with a great amount of skepticism. In the meantime, many older people had already accepted as a law of nature that each program is bound to contain bugs. The skepticism, however, was not without reason. To start with, it was not clear what form such correctness proofs could have. And if you never studied formal verification, just try and imagine to yourself how you would prove that a program is correct. You cannot build a proof on quicksand. You must have axioms. In this case, an axiomatic definition of the semantics of the programming language in which the program has been expressed. It was only after a few efforts that a technique for semantic definition emerged that could serve as a possibly practical starting point for correctness proofs. And here Dijkstra is referring to Floyd's method, the method which R.W. Floyd introduced in his paper on assigning meanings to programs, then which was picked up by Hoare and Dijkstra and developed further. When people then tried to give correctness proofs for existing programs, the result of that effort was very disappointing. The proofs were so long, hairy, and clumsy that they failed to convince, and this disappointment can still be traced in the skepticism of many. And in general, even today, if you tell people that formal verification is the future, they tend to really, those who are in the know or who have some experience of verification tend to say it's way too complicated, it's impractical, it will never work. Now Dijkstra says, on the other hand, that 3 discoveries have changed the scene since then. The first discovery was that the amount of formal labor needed to prove the correctness of a program could depend very heavily on the structure of the program. And this is what we call Dijkstra's second law. And his point here is that if you try and make a program, well, we'll come back to this. The second discovery was that of a few useful theorems about program constructs, and thanks to them we no longer needed to go all the way back to the axioms all the time. The most drastic discovery, however, was the last one, that what we then tried, namely to prove the correctness of a given program, was in a sense putting the cart before the horse. And what he means here is that what was being attempted was, we have these programs. You have a program, it's already working. You take the Linux kernel, you take even a simpler program, maybe take curl, which is a substantial program. If you try and prove the correctness of such a program directly, it turns out to be very hard. And Dijkstra says it's hard because you're putting the cart before the horse. A much more promising approach turned to be letting correctness proof and program grow hand in hand. With the choice of the structure of the correctness proof, one designs a program for which this proof is applicable. The fact that then the correctness concerns turn out to act as an inspiring heuristic guidance is an added benefit. So what he's saying is, if you start with a program that's already built without formal methods, without an attempt to prove its correctness, and you try and now strap on the proofs, your work becomes very hard. But if you construct the program intending to prove it's correct, and beginning by asking yourself, well, what will the proof look like? And then reasoning backwards from that proof to what the program must be, you get a lot of heuristic guidance, and the work of proving is not as hard as it would be. And this is the core insight, and this is what I think. I don't really know why he separates this insight from this one here. To my mind, I think this is very much a corollary of this, and they're the same principle, and they're what we call Dijkstra's second law, which is that if you understand the program, you can prove it. You can prove it to be correct. So it's the proof rests on your understanding of why the program is correct. And if you want to practically prove the correctness of a program, what you have to do is you have to make it understandable. And these two are not separate things. They're two sides of the same coin, understanding and certainty and proof and correctness. So uniting the two actually makes it so that the correctness proof of the program does not become a case of combinatorial explosion where you have to bring to bear all this compute and hope that you're going to, by brute force, prove the program to be correct. That's the wrong way to look at it. The right way to think about it is, I know why this program is correct, right? So I need to construct the program with a view to being able to show that it's correct. And when you do that, you find you can really get elegant and clean proofs, and it's not as hard as it sounds. If I ended this article, Dexter says, with the optimistic note, I could create the wrong impression that now the intrinsic difficulties of programming have been solved, but this is not true. The best I can say is that now we have a better insight in the nature of the difficulties of the programming task than a few years before. In my closing paragraphs, I hope to convey this nature, at the same time sketching the intellectual demands made upon the competent programmer. A programmer, and now here we get an illustration from Dijkstra, or a description from Dijkstra of why programming is so hard and what a programmer must be. So if you really actually want to understand what it takes to be a real programmer, this is it. A programmer must be able to express himself extremely well, both in a natural language and in formal systems. The need for exceptional mastery of a natural language is twofold. Firstly, it is not uncommon that, e.g., English is a language in which the problem is communicated to him and in which he must describe his interpretation or modification of the problem. This circumstance has been a source of many misunderstandings to the extent that there is a widespread belief that, e.g., English by its very nature is inadequate for that communication task. I don't believe it, although sloppy English certainly is. On the contrary, I have the feeling that our natural language is so intimately tied with what we call understanding that we must be able to use it to express what we have understood. That's the first thing. A programmer is a communicator. You're the interface between the formal world, the machine, and the outside world, which operates in ordinary human language. So you really have to be very good at communicating in that natural language to understand even what's being given to you. Secondly, we should not close our eyes for the fact that formalization, in a sense, is always after the fact, and that therefore natural language is an indispensable tool for thinking, in particular when new concepts have to be introduced. And this is what a programmer has to do all the time. He has to introduce new concepts, not occurring in the original problem statement, in order to be able to find, to describe, and to understand his own solution to the problem. For instance, when asked to construct a detector analyzing a string of characters for the occurrence of an instance of the nicely formally defined syntactic category sentence, he may find himself led to the introduction of a completely new syntactic category, proper begin of a sentence, i.e. a string of characters that is admissible as the opening substring of a sentence, but not yet a complete sentence itself. And having established that this is indeed a useful concept for the characterization of some intermediate of the computational process, he will proceed by manipulating the given formal syntax in order to derive the formal definition of this new syntactic category. In other words, given the problem, the programmer has to develop and formulate the theory necessary to justify his algorithm. In the course of this work, he will often be forced to invent his own formalism. And this is what Dijkstra is saying here. It's a bit terse, but what is he saying? He's saying that if you think about what you do when you're programming, perhaps you're writing a parser for some kind of string sequence that's there, and say it begins with say you're passing text and you want to search for strings that are contained in double quotes, right? But you want to distinguish the parts that are contained in double quotes from the parts that are not contained in double quotes. You may come up with something like two different modes, and you say in one mode you're unquoted, in another mode you're quoted. So you constantly invent new terms, new structures, new words, and this is a lot like the work of a formal mathematician. You have to come up with new names for concepts, and this is why learning to name variables, functions, and concepts really well is close to the essence of what it means to be a good programmer. It is so unbearably hard to name things well. And if you don't see this, then you haven't really begun to program well. You haven't seen how hard it is. Such demands as we draw to a close here, of course, are common to most mathematical work, but there are reasons to suppose that in programming they are more heavy than anywhere else. For besides the need of precision and explicitness, the programmer is faced with a problem of size that seems unique to the programming profession. When dealing with mastered complexity, the idea of a hierarchy seems to be a key concept. But the notion of a hierarchy implies that what at one level, hierarchy means like levels of abstraction. But the notion of a hierarchy implies that what at one level is regarded as an unanalyzed unit, at one level of abstraction, is regarded as a composite object at the next lower level of greater detail, for which the appropriate grain, say of time or space, is an order of magnitude smaller than the corresponding grain appropriate at the next higher level. As a result, so for example, he's saying you may have a module that you call inside a loop. So the loop is the function that you're calling inside this loop. If you think about those two levels of abstraction, at one level, you call this function, and it's just a single function in the loop body. And so it's just one operation among many, but it's running maybe hundreds or thousands of times. But then at the next lower level, it's a function, and that function just has one meaning. So there could be an order of magnitude in terms of the grain or in terms of the number of computations that are actually occurring if you think about the caller and the called function. You could have a caller that's calling a function and causing it to occur even 1,000 times, which is 3 orders of magnitude. For each invocation of the caller, you may end up invoking this called function 1,000 times. As a result, the number of levels that can meaningfully be distinguished in a hierarchical composition is kind of proportional to the logarithm of the ratio between the largest and the smallest grain. He means like of computation. In programming, where the total computation may take an hour, while the smallest time grain is in the order of microsecond, and today it's certainly much, much faster than microsecond. If we're talking about teraflops, surely that means, let's think about this. Teraflop, what is one? I think it's probably femtosecond. I'm not even sure. Let's see. Femtosecond. I think that's 10 minus 15. Yeah, so it's not femtosecond. It's the next one after femtosecond. This would be picoseconds. So today we have picoseconds on normal machines, the machines that you have at home. We're not talking about what OpenAI and Anthropic are running. Can easily exceed 10 to the 9th, a billion times. And here we are talking about a trillion times. We have an environment in which this ratio in programming can easily exceed 10 to the 9th, and I know of no other environment in which a single technology has to encompass so wide a span. It seems to be the circumstance sketched in the above paragraph that gives programming as an intellectual activity some of its unique flavors. The concepts he introduces, he means the programmer, must be highly effective tools for bringing the necessary amount of reasoning down to an amount that can be done. So just think about this. You may be writing a program that at the highest level is running on the scale of minutes, hours, even days, right? And then as you go down the levels of abstraction, down to functions which maybe invoke the standard library, those could be running thousands, hundreds of thousands, or millions of times, or billions, or even, like we've said, trillions of times per second. So the ratio between what's happening in your main function and what's happening in far lower levels of abstraction, 10 layers of abstraction down, could be trillions, could be quadrillions. And so you have to create a formal structure that allows you to think about all these layers correctly. And this shows that programming is an enormously difficult activity. The concepts he introduces must be highly effective tools for bringing the necessary amount of reasoning down to an amount that can be done. And also, the formalism he chooses must be such that his formulae do not explode in length, a regrettable phenomenon that is bound to occur unless the programmer pays conscious care to Let's just see in the text over here. Conscious care to measures for avoiding that explosion. A final consequence of the hierarchical nature of his artifacts is the competent programmer's agility, with which he switches back and forth between various semantic levels, between global and local considerations, an ability that has been described as a mental zoom lens. This agility is bewildering for those that are unaccustomed to it. And you know this, you see an error, message in your program, and you know it's in this specific function that I need to just add one if condition and then this won't happen. But you see what you're doing. You're passing in your mind perhaps 12 orders of magnitude, or even 15 or 18 orders of magnitude in an instant, and you even know what's happening here, and you're able to correct the program and reliably actually deploy it, and it works. If, and I hope that I am fair, I confront this with my impression of the standard mathematical curriculum, whatever that may be, I come to the following differences in stress between programming and mathematics. In the standard mathematical curriculum, the student becomes familiar, sometimes even very familiar, with a standard collection of mathematical concepts. So mathematicians learn about algebra, they learn about groups and rings and fields and things like this, and they learn about calculus, and they learn about mathematical analysis more broadly, and number theory. So there's a common body of knowledge which most mathematicians who are, let's say, even at a graduate level, are all familiar with more or less. There's this common body of knowledge that they all have. That's in mathematics. He is less trained, that is the mathematician, in introducing new concepts himself. So mathematicians tend to study for a long time the old concepts, and for good reason. They may not be as good as introducing new concepts that are useful. In the standard mathematical curriculum, the second point, the student becomes familiar, sometimes even very familiar, with a standard set of notational techniques. So you know how to use a sigma, how to use the integration sign, how to, you know all these notational techniques, how to take a limit, how to say if then, how to say if and only if, how the implication arrow works, and so forth. He is less trained in inventing his own notation when the need arises, which is what we do in programming. In the standard mathematical curriculum, the student often only sees problems so small, he means relatively small, that they are dealt with at a single semantic level. Which is to say, you don't see a lot of modularization in mathematics. You can go through an entire semester course, say in introductory analysis. Since I'm not a mathematician, I'm just talking about stuff that I've done. And you talk about limits, and you talk about functions, and you go on and on and on and on. But you don't have multiple layers of abstraction for the most part, or you have one or two layers of abstraction. You have nothing that corresponds to these 10 to the 12 layers of compute, or 12, 15 orders of magnitude, or layers of abstraction, 10 or 15 layers of abstraction, which will happen in a real production application. One function calls another, calls another, calls another. As a result, many students see mathematics rather as the art of organizing their symbols on their piece of paper than as the art of organizing their thoughts. And this is just because you're learning elegance within a very limited domain. But in programming, you have to become elegant at organizing extremely broad, extremely deep formal structures. If I have given some of my readers the first germs of the feeling that to an inventive and effective mathematician, the field of programming may provide the area par excellence, in which to find his challenge and bring his abilities to bear, one of my dearest wishes has been fulfilled. Eindhoven Technological University, 23rd May 1973. So what we learned from this, just briefly in conclusion, I would summarize this by saying, briefly, I put this briefly, this is a kind of half inaccurate statement, but sometimes it's good to be clear, and sometimes clarity requires that you state something a bit forcefully. Programming is harder than mathematics. Programming is more formal than mathematics. Programming is more mathematical than the mathematics that mathematicians do. their work, in a sense, is shallow and superficial when measured as formal. And I think that that doesn't mean that mathematicians are not more intelligent. I mean, many of them are far more intelligent than the best of us. Their work is much harder at the level of the individual grain. The individual units that they play around with, the structures that they deal with, are very hard to understand and take a lot of training and years to really understand. However, if you measure them as formal entities, you will find that then they can't really hold water to the difficulty of production programming systems. And so, as a programmer, you should really see the work you're doing as mathematical in nature and hard and very difficult. And so this is why you want to study formal verification, and that's what we're going to be doing in this channel. So stay tuned for more.